Hello everyone, so in today's video, we would now be solving for the influence line diagrams for shear at a specific point of a statically determinate beam. So before watching this video, it is a prerequisite for you to watch the previous video, which is part 1. Okay, so in this video, once again, we would be solving for the ILD for shear at a specific point. So in this video, we would be arbitrarily choosing this particular point here. So this point was chosen by random. So, okay, so we would now be determining the influence line diagram and we would be drawing it. And in order for us to do that, if this is now our frame, let us once again isolate this blue beam here in this manner. And in order for us to draw the influence line diagram, what we would be doing is that we will be placing a unit load at this portion, and then we would be solving for the reaction or the, not the reaction, but the result of the shear at this point if ever the load is here, 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 since we are to assume that this is a moving load. And if it is a moving load, of course, it would be moving in this direction. So again, what we will be doing is that we will be analyzing our beam and we will be solving for the resulting shear at this point if ever the what you call this load is here and for all of these locations here. Okay, so going back here, so the first thing that we will be doing, so how can we solve for the shear at this point? So our method here is that we will be cutting a particular section here. So we would be cutting the section here and we would be getting the summation of forces vertical. So that will now be the value for VC or shear at C. So our sign convention is upwards positive. So if you want to learn about this, better watch our previous video on frames and beams. Okay, so again, what we will be doing is that we will be cutting a section about the point C. Then we will be choosing one side, and in our analysis, we will be choosing the left side. Then again, we would be solving for the summation forces vertical, and whatever is the summation, that is now the value of shear at C. Okay, so in order for us to do that, if we would once again cut a section here, and we will be choosing the left side of our, what do you call this, of our beam or of our cut section, as you can see that we would now be having two vertical loads, 1 kilonewton and the value for AV. So as for the value of AV, let us solve for it first. So we would now be solving for the moment at point B. So moment at point B, that is equal to 0. And let us assume a sign convention of clockwise positive. So with that being said, as you can see here, AV. So AV, that is upwards. That is my assumed direction. So if it is upwards, it would cause a clockwise rotation about point B. So again, it has a tendency to rotate this beam in a clockwise direction. So from that, guys, that is now AV times the lever arm. So do not forget the lever arm since we are to deal with moment. That is AV times 10. So that is it basically for the moment due to AV. So aside from AV, we also have a moment here, or a moment as brought about this by this 1 kilonewton load, I should say. And since this 1 kilonewton load has a tendency to rotate this point in a counterclockwise direction, it must be negative. So negative 1 times, so what is now the lever arm? So the lever arm is once again the perpendicular distance from this point up until this point. So this is now that particular distance. So that is also 10 meters. So 1 times 10. So since there are no more loads present in our figure here, this is now equal to 0. Then solving for it, I would not make use of my calculator below me. Rather, you could do it your own, but the answer there is just 1 kilonewton. Okay? So after doing that, what we would be doing once again is that we will be cutting a section here. So after cutting a section, what happens there is that, of course, it would be cut. And upon cutting, this shear force would come out. So since we are only particular with the shear about that point, yun po yung kailangan natin, or that is what we actually need. Again, like what I have said earlier, that in order for us to get the shear about this point, VC, or the shear at C, is basically equal to the summation of forces vertical, considering that if we would be cutting a section here, we would only choose one direction, and that direction is the left side. Okay? So, don't mind this right side here, guys. We're only particular with this side. So, summation of forces vertical, let us assume upwards positive. So, from that, guys, VC is now equal to, so what are the forces here? So, we have here AV, which is upwards, and that is 1 kilonewton. So, that is 1 kilonewton minus 1 kilonewton load, which is downwards. So, from that, VC is now equal to 0. So with that being said, guys, if the load is located here, it means that the shear experienced by this point, or at this point, is equal to 0. So if we are to draw the ILD, so let's say that this is now our ILD, or influence line diagram, if the load is at this location, meaning the shear at C is equal to 0. So from that, guys, I will be plotting 0 here at this particular point. So take note that this is the ILD at C. Okay? So next up, we would now be moving this load. So you could move it at this location, it would be up to you, but it would be more efficient if we would now be moving it to this side. Okay? So up until our section C. Okay? So as you know that from the previous lecture, once we move the value for this unit load, the value for AV would also vary. So this is not equal to 1 kilonewton any longer. So in order for us to know, let us just solve for it. So again, same old method. Let us get the summation moment about this point. So summation moment B is equal to 0. Let us assume a sign convention of clockwise positive. So with that, we have here AV. So this would cause rotation about this point. And as you can see, this would cause a clockwise rotation. So AV, that is positive, times the lever arm of 10. Okay. So what forces do we have here that would cause rotation about point B? We still have the force 1 kilonewton, or the unit load. Okay, so that is now minus 1 kilonewton. And take note of the lever arm. If this here is the load, the lever arm is the distance, or the perpendicular distance, from this force up until this point. So if this is 10 meters, this is 2 meters, we could now say that this portion here is 2 meters, or 10 minus 8. Okay, so from that, guys, the lever arm here would now be equal to 2 meters. So solving for AV, so now looking at the calculator below me, or to your left, so let me just turn this on. So that is now 1 times 2 divided by 10. Okay, so that is 0.2. Okay, so AV is now equal to 0.2 kilonewtons. Okay, so however, guys, we are not really particular with AV. Though we need AV to solve for the value of the shear at C. Again, our ultimate goal here is for us to get the shear at C. So with that, guys, again, we would be cutting a section here at this part at a distance 8 meters from this point. And again, after doing so, in order for us to get the shear at C, that is basically the summation of forces vertical, upwards positive, from the section C to the left. Okay, so using this figure, we have here the force AV, that is upwards. So VC is now equal to AV, that is 0.2, and it is upwards. So 0.2, and we have here a 1 kilonewton load, which is downwards, so minus 1 kilonewton. And 0.2 minus 1 kilonewton, that would give us an answer of negative 0.8 kilonewtons. Okay, so from that, if the load is located here, so again, if the load is located here, it means that the shear experienced at C is equal to negative 0.8 kilonewtons. So if that is the case, guys, again, a while ago, we have plotted that if the load is located here, the shear was 0, if you can remember. And now, if the load is located here, the value of shear is negative 0.8. So from that, we would now be plotting negative 0.8. Okay? So that is now the first segment of our ILD. Okay, so next up, so I want to disclaim that the next method I will show you is erroneous, and I will want to show you in order for you not to commit the same mistake. Okay, so if you are thinking that after placing the shear at this point, so maybe the next point of interest would now be at this portion or at B. So again, you might do this soon, right away. Again, I want to disclaim that this is erroneous. I will explain to you later why. But if ever that you did this right away, so if you would now be getting the summation of moment B is equal to 0, clockwise positive. So what are the forces that would cause rotation about this point? So that is AV times 10. And that is positive once again since it is clockwise. Okay? So what else or what other forces would now cause rotation about this point? So as you can see here, this 1 kilonewton load is acting exactly at point B. It means that if we would be adding it here, so this is basically negative 1 kilonewton times the lever arm of 0. So this would just simply cancel out. Okay? So with that, guys, for the efficiency of our solution, I would not include it. So this is now equal to 0, I should say. And solving for the value of AV, that is now equal to 0. So take note, guys, that this is already equal to 0. So proceeding, upon cutting a section here, so summation of forces, vertical, upwards, positive. Do we have any forces here? So basically, guys, we do not have any forces present here because once again, this is equal to 0. So proceeding, we could now say that VC is now equal to 0 if the load is located here. Okay? So again, if the load is located here at this point, oh, by the way, before I proceed, so in the summation of forces vertical, why didn't we include the negative 1 kilonewtons or the unit load? So the reason why that is not included is that when we have cut a section here and we chose left, as you know that this unit load here is on the right, which is not included any longer because once again, we only chose one side. Okay, so proceeding. So again, if the load is located here, we have found out that the shear at C is equal to 0. So if we are once again to bring out our ILD, if you are to think of it this way, or if you are to proceed to this point immediately, if the load is here, meaning that the shear at C is equal to 0, so meaning that we will be plotting the value here, okay? So again, I want to reiterate that this is actually erroneous. So again, if you would be doing it that way, this is now your ILD, okay? And again, so for the nth time, I want to disclaim that this is rather erroneous. And the reason why I am teaching this to you is in order for you not to commit the same mistake as I did back in college. Okay, so again, this is once again erroneous for the nth time. So where did we go wrong? So doon lang po tayo nagkamali sa isang part lang po. Okay, so we will be backtracking, guys. So let us now erase this line here and let us bring this 1 kilonewton load back to point C. So again, we would now be bringing this back to point C, which we have already solved for a while ago. But what if, for example, that for this particular load, we are to move this by a tiny bit to the right? So let's say by 0.000000001 millimeters, or even less, a microscopic distance. So again, if you would be doing that, guys, we will be moving it by a bit. So let me just go back here. Again, look at the figure. So it would move by a tiny bit. Okay, so what happens if that would be the case, or if you would be moving it by a tiny bit? So as for the resultant, it would actually be the same. So if we would be solving for the force AV or for the support reaction AV, we would be getting the moment about this point, or moment at B, that must be equal to 0. And our sign convention, once again, is clockwise positive. So proceeding. So from that, AV times 10, same old. So that is positive since it would rotate this beam in a clockwise direction, minus 1 kilonewton. And what is now its lever arm? So for its lever arm, guys, so for the lever arm, if this is 8.0001 and the like, this distance here, apologies, so this distance here, I should say, this is 1.999999 repeating, okay, which is basically still equal to 2. Okay, so if you would be rounding that to the nearest number, that is now 2. So same old, so times 2. So this is now equal to 0, and from that, guys, we would still have the same answer, which is the answer for the calculator below me. Okay, so if that is 0.2 kilonewtons, so if it is still the same, what would change in our instance right now? So take note, guys, that once again, we have moved this 1 kilonewton load a tiny bit to the right. So if in order for us to solve for the shear at C, we would once again cut the section at C. But if I am to zoom in here, take note, guys, that the value for C, or this unit load here, is not included in our analysis any longer. So again, if I am to zoom in here, as you can see, guys, that it is now not included in our analysis because it has moved a tiny bit. So from that, guys, we will now be removing that part. Okay, so we have already removed the 1 kilonewton load. Okay, so solving now for the value of shear. So shear at C is equal to the summation of forces vertical considering our work cut section C. So VC is now equal to AV, which is 0.2 kilonewtons, minus, well, actually, we would not once again include this 1 kilonewton load. So basically, that is already our answer. So 0.2 kilonewtons. So from that, we would now be plotting our updated ILD. So for our ILD, if the 1 kilonewton load is located at this part, still at 8 but a little bit to the right, so the value of the shear at C, if the 1 kilonewton load is here, that is equal to once again 0.2 kilonewtons. So if 0.2, we would be plotting it here. So this is now 0.2 kilonewtons. And we would be tracing from this point to 0.2 kilonewtons. And there, and if you can remember a while ago, if you would be moving our load to this direction, so in our analysis a while ago, the value for VC is equal to 0. If you can remember from our erroneous detail a while ago, so where was that? Let me just show you. So again, a while ago, again, this is erroneous. If the load is here, the value for ILD, or for the value for VC if the load is at this point, that is now equal to 0. Okay, so proceeding, 0. So this is now our correct influence line diagram for shear at C. Okay, so what does this mean? So meaning, if you would be looking at the diagram, if the load is located at this point, it means that if the load is located at this point, it does not really affect the shear at C, or the shear is basically equal to 0. Okay, so if let's say that your load is located here, so if your load is located here, it would experience this fraction or this multiplier of the shear, or it would now experience a negative shear. If the load is here, it would now experience a positive shear. So suppose that we would now be comparing. So which is the more critical value? Would it be if the shear is here, or the force is here, I should say, or if the force is here? So if we are to project this vertically downwards, so this is the graph, or this is the y coordinates of the graph if the load is here. And if the load is here, this is now the y component of the ILD. So visually looking at it, kind of redundant, but with that being said, or what I want to tell you is that if the load is located somewhere here, it would actually greatly affect the shear at C as compared if the load is somewhere here. So meaning guys, the dangerous area is actually at this location. And this location would now give you the maximum value for the shear. Okay? So what if, for example, you are given this load? So if you are given this load diagram, as you can see here at the top, we have here a 50 kilonewton load, a 25 kilonewton load, and a 5 kilonewton per meter uniformly distributed load. In order for you to solve for the shear at C, so if you want to solve for the shear at C, if you want to do it the long way, or the statics way, just cut a section here, then, well, solve for the shear at that point. But since we have already indicated, or we have already determined the ILD, let us now make use of the ILD in order for us to solve for the shear at C given these loads. So what we would be doing next is that we would be projecting them vertically downwards. And upon projection, guys, we would now solve for these values. So again, in order for you to remember, these loads here at the bottom part, or this 0.2 kilonewton load here and this negative 0.8 kilonewton shear here, these values were solved using a 1 kilonewton load. And as you can see that for our loads at the top, we are not making use of the 1 kilonewton load any longer. Mas mataas na. 50 kilonewtons na yung gamit natin ngayon, hindi na 1 kilonewton. So what we would be doing is that we would just multiply 50 kilonewtons to whatever the value is here. So what that means is that, as you know, that whatever the value is here, if ever that this load here is equal to 1 kilonewton, by ratio and proportion, alam mo na po dapat kung ano yung resultant dito, or kung ano yung shear dito. But the thing is, once again, this is not 1 kilonewton. In this case, we have 50 1 kilonewton loads. Okay? So again, this value here is equal to 50 times 1 kilonewtons. So from that, guys, whatever this value is, we must multiply it by 50 in order for us to know what is its effect in solving for the value for the shear. Okay? So, again, with that, I should say, apologies. So I will be naming this value here, or this height here, as y1. I will name this as y2, and I will name this as y3. Okay, so though there are calculator techniques in solving for those values using static mode and using regression analysis, I would rather do it the old school way in order for you to get a better glimpse of what we are doing. So what I would be doing in order for me to solve for the value of y1 is that I would just be solving for it via ratio and proportion. So the ratio of the bigger triangle, which is this one here, so this is the bigger triangle, its ratio is equal to the ratio of the smaller triangle. Okay? So their slopes are basically the same. So from that, guys, so for the bigger triangle, its vertical component is negative 0.8, so negative 0.8, divided by, what is its horizontal distance? That is 8 meters. So negative 0.8 divided by 8 meters, this is now equal to, so what about for the ratio of the smaller triangle? So for the smaller triangle, we have here y1 divided by whatever this dimension is. So from that, this is 2 meters. So 2 meters. Then solving for the value of y1, this is now equal to, so by our calculator, so negative 0.8 times 2 divided by 8. So the value of y1 is equal to negative 0.2. Okay? So negative 0.2. So meaning, if ever that we only have this load here, we do not have these values or these loads, the shear at C should have been just 50 times negative 2. So meaning, guys, due to this load here, the shear at C is experiencing a negative 100 kilonewton internal force. Okay? But the thing is, that is not just the load. Okay? So we still have this load here and this load here, and from that, we should also take them into consideration. Okay, so let me just remove my mess here. Okay, so for the value of y2, so same old, the slope of the bigger triangle, that is equal to the slope of the smaller triangle. So for the smaller triangle, which is this part here, so its vertical component is y2 divided by, for its horizontal distance, it is not just 3.5, okay? It is the whole distance of the smaller triangle, and that is 2 meters plus 3.5, and that is 5.5. So solving for the value of y2, that is now equal to, so looking once again at the calculator to your left, that is negative 0.8 divided by 8 times 5.5. The answer there is negative 0.55. Okay, so let us proceed to the next slide here. So basically, again, that is negative 0.2, negative 0.55, negative 0.8. So what about for this one here? I forgot to solve for it. So what about for this dimension here? What about for y3? So take note, guys, for the location of y3, that is 1.33 meters from this portion. And then for this triangle, this is now equal to 0.2 kilonewtons by 2 meters. Okay, so proceeding to the next slide here. Again, this is 2 meters. And this here is 1.33. So solving for y3. So y3 divided by 1.33 via ratio and proportion, that is equal to positive 0.2 divided by 2. So from that y3, if I'm not mistaken, this should be 0.133. So looking at the calculator, so that is 1.33 times 0.2 divided by 0.2, that is 0.1, divided by 2, I should say. So that is 0.133. Okay? So if I am to erase everything, this is equal to 1.33. Okay, so if that is 1.33, let us now solve for the reaction considering all of these loads. Okay, so our approach here is that we would be multiplying this 50 kilonewton load to this value. Then we would be multiplying this 25 kilonewton load to this value, which is basically 0. What that means is that this load here does not really affect the shear at point C. So it really doesn't matter if it is here or not. Okay? So from that, guys, for the next one, for the uniformly distributed load, what we will be doing here is that we will be projecting this downwards. So as you can see, this is now the values. And we would just be multiplying this 5 kilonewton per meter load to these areas here. Okay? So from that, guys, the shear at C, so C is now equal to 50 times negative 0.2. Then I will be multiplying this value, 5 kilonewton per meter, to this area here. So, plus 5 kilonewton per meter times the area of the trapezoid. So if you can remember the area of the trapezoid, that is basically equal to height 1 plus height 2 divided by 2 times the length, or the averages of these dimensions, the average of them multiplied by the length. The thing is, I forgot the dimension. So let me just go back here. So this dimension here is equal to, so that is now, if this is 5.5, this here is 8 minus 5.5. Okay, so 8 minus 5.5. So this distance here is equal to 2.5. Okay, so this is 2.5. Since this is 8 meters from this point to this point, then this is 3.5, this is 2. So 8 meters minus 3.5 minus 2 meters, that would give you an answer of 2.5 meters. And as for this distance here, okay, so as for this distance here, if this is 3.17, so this is 2.5, 3.17 minus 2.5. So from that is, once again, 3.17 minus 2.5. So 0.67. So going back to our last slide here. So this is, nalimutan ko na naman. So that is 2.5.67. So, oops, sorry. So this is 2.5, and this here is 0.67. So from that, guys, 5 times, I would be segregating the two areas, I think. So I would be considering this area first, so I will be naming this as area 1. So again, the value or the area for area 1, that is the averages or the averages of these two heights times the length. So that is negative 0.55 plus negative 0.8 or minus 0.8 divided by 2 times the length of 2.5. Okay, so that is for this particular effect. So for this projection here. Okay, so for this one, for let's say, I will be naming this as area 2, this is plus 5 kilonewton per meter times, again, the averages of the two dimensions. So if you have here 1.33, and we have here, sorry, this is not 1.33, this is 0.133, I should say. And for this height here, this is positive 0.2. So from that is 0.2 plus 0.133 divided by 2 times 0.67. This is basically area 2. And this is area 1. Okay, so what about for this one here? Again, what I have said earlier, that this value will not really affect, or this load here will not really affect the shear. Okay? So this is plus 25 kilonewtons times, if you would be projecting it, so if you would be projecting it, its value is equal to 0. So times 0. Okay, so from that, the value of VC is now equal to, so looking at the calculator, so 50 times negative 2, negative 0.2, I should say, plus 5 times negative 55, negative 0.55 minus 0.8 divided by 2 times 2.5 plus 5 times 0.2 plus 0.133 divided by 2 times 0.67 plus 25 times 0. Okay, so from that, the answer for shear at C is equal to negative 17.88 kilonewtons. So this is now the value for VC, considering our solved ILD earlier and this loads or these actual loads. So there.